Welcome back to Module 3. Today we tackle one of the most critical and frequently misunderstood challenges in professional AI deployment: hallucinations. If you've ever asked an AI assistant for a fact, gotten a confident, fluent answer, and later discovered it was completely fabricated, you've witnessed a hallucination firsthand. And if you're building AI-powered systems for real business use cases, you already know this isn't just an inconvenience, it's a liability. This session is called Engineering AI Reliability, because that's exactly what we're doing. We're moving beyond surface-level prompting and into the technical architecture of trust. By the end of this session, you'll understand why hallucinations happen at a fundamental level, how researchers categorize and measure them, and most importantly, what a production-grade mitigation stack looks like. This is the session where theoretical AI knowledge becomes engineering discipline. Let's get into it.
Let's define the problem precisely. In AI, a hallucination occurs when a model generates text that is fluent, coherent, and confident, but factually incorrect or entirely inconsistent with reality. The key word here is fluent. This is what makes hallucinations so dangerous. The model doesn't stutter, it doesn't express doubt, and it doesn't flag uncertainty. It delivers fabricated information with exactly the same confident tone it uses for true information. From a reader's perspective, there's no signal that something has gone wrong. I want you to think of a large language model as a brilliant but amnesiac professor. This professor has read every textbook, every journal, every web page. They've internalized a staggering amount of knowledge. But here's the catch. Their memory is lossy. They can't always recall specific facts with precision. So when asked something they're not fully certain about, instead of saying, "I don't know," they confabulate. They fill the gap with a plausible-sounding story that fits the shape of what they do remember. That's not dishonesty. It's a structural limitation. And understanding that it's structural rather than incidental is the first step toward engineering around it. You can't shame a model out of hallucinating. You have to build systems that compensate for it.
To fix hallucinations effectively, we need to categorize them. Not all hallucinations are the same, and different types require different mitigations. The primary split is between intrinsic and extrinsic hallucinations. An intrinsic hallucination directly contradicts the source material you provided. You give the model a document, ask it to summarize, and it produces a summary that contradicts facts clearly stated in that document. The model had the right information in context and still got it wrong. An extrinsic hallucination is different. Here, the model fabricates information that simply wasn't present anywhere, not in the context, not in reality. Invented citations, made-up statistics, fictional court cases cited as real precedents. These are the hallucinations that make lawyers nervous. The second dimension of this taxonomy is factuality versus faithfulness. Factuality asks, does the output match ground truth in the real world? Faithfulness asks, does the output stay consistent with the specific documents and context provided? These two dimensions often overlap, but they don't always. A model can be faithful to a source document that itself contains errors, making it factually wrong but technically faithful. This distinction matters enormously when you're designing evaluation pipelines, because a single metric won't capture both failure modes. You need separate checks for each.
Here's a sobering truth that changes how you approach this problem. Research strongly suggests that hallucinations are a theoretically inevitable feature of large language models. Not a bug that will be patched in the next release, a fundamental property of how these systems work. The reason comes down to information compression. An LLM is trained by compressing an enormous corpus of human knowledge, trillions of tokens, into billions of floating point parameters. That compression is inherently lossy. You cannot store all of human knowledge without loss in a finite set of weights. Specific details, rare facts, precise citations, these are exactly the kinds of things that get smoothed over during compression. What the model retains are statistical associations. It learns that certain words tend to follow certain other words in certain contexts. It learns the shape of knowledge rather than the content of knowledge. When you ask it a specific factual question, it doesn't query a database. It generates the most statistically plausible completion given its training distribution. The practical implication is this. If you're building a system where factual accuracy is mission critical, legal research, medical information, financial analysis, you cannot rely on a model's parametric memory alone. The architecture must externalize the knowledge. That's the foundation of everything else we'll discuss today.
Let's go deeper on the root causes. There are 5 primary drivers of hallucination, and the first 2 are about training data and the model's probabilistic nature. Root cause 1 is training data quality. These models are trained on the web, and the web contains a lot of misinformation, outdated facts, contradictory sources, and low-quality content. When the model learns from this data, it doesn't filter for truth. It learns frequencies and associations. If a misconception appears frequently enough in training data, the model will repeat it confidently. The knowledge cutoff compounds this. A model trained through a specific date has no knowledge of events after that date. Ask it about recent regulatory changes or the latest research, and it will either admit ignorance, if it's been trained to do so, or it will fabricate something plausible based on patterns it learned before the cutoff. Root cause 2 is probabilistic architecture. This is the deepest cause. At inference time, the model is not looking up facts. It is sampling from a probability distribution over possible next tokens. When the model is certain, the high probability token is clearly correct. But when it's uncertain, the sampling process doesn't produce an "I don't know." It produces whatever token had the highest probability in that moment, which might be a confident-sounding fabrication. The model has no built-in mechanism that says, my confidence is below threshold, I should refuse to answer. That behavior has to be trained in explicitly, and we'll cover how in a few slides.
The third root cause is something you have direct control over, decoding parameters, specifically temperature and top P, the settings that control how the model samples from its probability distribution. Temperature is a scaling factor applied to the output distribution. At a temperature of 0, the model always picks the single highest probability token, fully deterministic and maximally conservative. As temperature increases, the distribution flattens, and lower probability tokens become increasingly likely to be selected. High temperature means creative, diverse, surprising outputs. It also means a dramatically higher rate of hallucination because you're actively sampling from the uncertain tail of the distribution. Top P, also called nucleus sampling, works differently but has a related effect. Instead of scaling the distribution, top P sets a cumulative probability threshold. The model samples only from the smallest set of tokens whose combined probability exceeds that threshold. A low top P value, like 0.5, restricts sampling to the most confident, high-probability tokens. A high top P value, like 0.95 or higher, allows the model to sample from the long tail of the distribution, the low-probability tokens where the model is least certain and where fabrications most commonly originate. The practical takeaway for production systems is clear. When accuracy matters more than creativity, lower your temperature and tighten your top P. These aren't just style settings, they're reliability controls. For factual, high-stakes applications, temperatures of 0.1 to 0.3 and top p-values under 0.7 are a common starting point.
Now we move to mitigations, and the first and most powerful mitigation is retrieval-augmented generation, or RAG. The core insight behind RAG is elegant. If hallucinations happen because the model relies on its imperfect internal memory, then don't let it rely on internal memory. Instead, retrieve verified authoritative information at inference time and inject it into the context. The model's job shifts from remembering facts to synthesizing information it has just been given. Here's how it works in practice. When a user submits a query, a retrieval system searches a curated knowledge base, your company's documentation, verified databases, authoritative sources, and returns the most relevant passages. Those passages are included in the prompt alongside the user's question. The model then generates a response grounded in that retrieved content, rather than its parametric memory. The numbers back this up decisively.
Research shows that RAG can reduce hallucination severity by up to 85% compared to baseline models operating from memory alone. That's not a marginal improvement, that's a transformation. And crucially, RAG decouples the model from a fixed knowledge cutoff. Your knowledge base can be updated continuously. New regulations get added tonight, and tomorrow the model answers questions about them accurately, without any retraining. RAG is the foundational mitigation layer in virtually every serious production AI system. We covered it in depth in session 2.3, and now you understand precisely why it was worth an entire session.
The second mitigation is fine-tuning for calibration, and this one addresses the problem at its source, the model's own behavior when it doesn't know something. The goal of calibration fine-tuning is to teach the model to accurately represent its own uncertainty. A well-calibrated model, when it genuinely doesn't have reliable information, should say so, clearly and specifically, not with vague hedging, but with explicit acknowledgement, I don't have reliable information on this specific question, or my training data may not include recent developments in this area. The way this is trained into the model is straightforward in concept, but requires careful dataset construction. You include examples in the fine-tuning dataset where the correct response to a factually uncertain question is an explicit, I don't know, or a calibrated uncertainty statement. By reinforcing these responses during training, the model learns that admitting uncertainty is rewarded behavior. This matters because the opposite behavior, confident confabulation, is what gets learned by default from internet-scale text. On the internet, confident-sounding answers are everywhere. Appropriately uncertain answers are comparatively rare. So the base model defaults to confidence even when it shouldn't. Calibration fine-tuning also helps with what researchers call hallucination frequency versus severity. Even when a model does produce uncertain information, a well-calibrated model will flag it, giving downstream guardrails and human reviewers a clear signal to verify before acting. That's enormously valuable in high-stakes workflows.
The third mitigation moves from data-level training to feedback-driven alignment, reinforcement learning from human feedback, and its evolution, constitutional AI. RLHF works by training a reward model on human preferences. Human raters evaluate model outputs and score them, preferring accurate responses over fabricated ones, clear uncertainty acknowledgement over false confidence. The language model is then fine-tuned using reinforcement learning to maximize these reward scores. The result is a model that has been directly optimized to produce the kinds of responses humans judged as accurate and trustworthy. Research data on RLHF's effectiveness is compelling. It can reduce factual errors by up to 40% compared to models trained without this feedback loop. That's a substantial reduction from a process that requires no changes to the model's architecture, just a smarter training signal. Constitutional AI, pioneered by Anthropic, takes this a step further. Instead of relying solely on human ratings, which are expensive to collect and can be inconsistent, constitutional AI defines a set of explicit principles the model must follow. These might include, do not state facts you are uncertain about as if they were confirmed, or acknowledge when a question falls outside your reliable knowledge. The model is then trained to critique its own outputs against these principles and revise them. It becomes, in a sense, its own editor, applying a set of truth-first standards before finalizing a response. This reduces the human labor cost of RLHF while encoding explicit reliability standards directly into the model's behavior.
The fourth mitigation is something you can deploy immediately without modifying any model or infrastructure: prompt engineering for accuracy. The way you structure your prompt has a measurable impact on hallucination rates. There are 3 specific patterns worth internalizing. The first is explicit uncertainty instructions. Simply telling the model, if you are not certain, say so explicitly, makes a real difference. The model has been trained to respond to instructions, and this is a valid instruction. Adding phrases like, do not speculate, only include information you are confident about, or acknowledge gaps in your knowledge rather than filling them, activates behaviors that exist in the model but aren't always expressed by default. The second pattern is conciseness constraints. This one is counterintuitive but empirically supported. Shorter responses hallucinate less. Every additional token the model generates is another opportunity for the statistical sampling process to drift toward fabrication.
When you constrain the model to a specific length or format, answer in no more than 3 sentences, respond only with confirmed facts, you're reducing the surface area for error. The third pattern is mandatory citation requirements. When you require the model to cite a specific source for every factual claim it makes, it is forced to ground its output. If it cannot provide a source, it should not make the claim. This doesn't eliminate hallucination. A model can fabricate a citation just as easily as a fact. But combined with RAG and verification layers, citation requirements significantly tighten the accuracy loop. These 3 patterns stack. Using all 3 together creates substantially more accurate outputs than using none of them.
The fifth mitigation operates as a post-generation safety layer, output guardrails. This is where systems like NVIDIA NeMo guardrails come in. The core problem that guardrails solve is this. No matter how well you've prompted, fine-tuned, and grounded your model, individual responses can still fail. A single bad response reaching an end user in a legal, medical, or financial context can have serious consequences. Guardrails provide a structured checkpoint between model output and user delivery. Here's how a system like NeMo Guardrails works in practice. Rather than sending a single response directly to the user, the system generates multiple candidate responses, often 3 to 5. Then, a separate LLM-based evaluation layer, sometimes called an LLM judge, scores each candidate for internal consistency, factual grounding, and policy compliance. Internal consistency checking is particularly valuable. If the model claims X in one sentence and contradicts X in another sentence, that inconsistency is a reliable signal of a hallucination or a reasoning failure. The judge flags it, and that response is blocked rather than delivered. Responses that pass the consistency and grounding checks proceed to the user. Responses that fail are either blocked entirely, triggering a fallback response, or returned to the model with the failure reason for revision. This approach adds latency. You're generating multiple responses and running an evaluation pass, but for production systems where reliability is non-negotiable, that latency trade-off is almost always worth it. The cost of a single bad output in a high-stakes context far exceeds the infrastructure cost of thorough validation.
Beyond reactive guardrails, there's a class of techniques called active detection, methods that probe the model's own consistency to detect hallucinations before they surface. The most elegant of these is SelfCheckGPT. The intuition behind it is simple but powerful. If a model truly knows a fact, if that fact is robustly encoded in its parameters, it should report it consistently, regardless of how you ask or what sampling randomness is in play. A real fact reproduces reliably. A confabulation is fragile. Here's how SelfCheckGPT operationalizes this. Rather than generating a single response, the system queries the model multiple times for the same factual question, typically 3 to 5 times, with non-zero temperature to introduce sampling variation. If the model produces consistent answers across all samples, that consistency is a strong positive signal for factual reliability. But if different samples produce meaningfully inconsistent answers, the model says the event happened in 2019 in one sample and 2021 in another, or attributes a quote to different people, that inconsistency flags the response as a likely hallucination. The system can then route that response for human review, refuse to deliver it, or trigger a retrieval fallback. SelfCheckGPT is particularly valuable in settings where you don't have a ground truth knowledge base to retrieve from, rare domains, emerging topics, or proprietary information. In those cases, you can't use RAG because there's no corpus to search, but you can still detect low-confidence fabrications through consistency probing. It's a useful tool in the detection layer of your reliability stack.
Now we bring it all together. The research literature is unambiguous. No single mitigation is sufficient. The strongest systems use a layered architecture, defense and depth applied to AI reliability. A 2024 Stanford study quantified just how powerful this combination can be. The study examined the effect of stacking 3 mitigations. We've covered RAG for grounding, RLHF for behavioral alignment, and Guardrails for post-generation validation. The result was a 96% reduction in hallucinations compared to the unmitigated baseline. 96%. Let's think about what that means architecturally. RAG handles the information access problem. The model isn't relying on memory for facts, it's reading from verified sources. RLHF handles the behavioral problem. The model has been trained to prefer accuracy and express uncertainty rather than confabulate. Guardrails handle the residual error problem. Even when the first 2 layers work perfectly, the third layer catches what slips through. Each layer targets a different failure mode, and because the failure modes are different, the layers are largely independent. A failure that gets past RAG might be caught by RLHF calibration, and if it survives that, the guardrail judge detects the inconsistency. This is why defense in depth is the gold standard for high-risk domains like law, medicine, and regulated financial services. In those domains, even a 4% residual hallucination rate may be unacceptable for some use cases, and you'd add further layers like human review checkpoints for the highest stakes decisions. But for most enterprise applications, a 96% reduction transforms AI from a liability risk into a reliable operational tool.
Let's consolidate what you've built today into a durable mental model. Hallucinations are not a bug waiting to be fixed. They are an architectural property of probabilistic language models, a direct consequence of lossy compression, statistical generation, and the fundamental challenge of encoding knowledge without ground truth verification. That's the honest engineering reality. But here's the equally important reality. They are manageable, not eliminated entirely, managed, measured, and reduced to levels that make AI systems genuinely trustworthy for professional deployment. The mitigation stack is a layered defense. RAG grounds the model in verified external knowledge, eliminating the memory problem for domains where a knowledge base exists. Fine-tuning calibration teaches the model to express uncertainty rather than confabulate. RLHF and constitutional AI align the model's behavior toward accuracy at the training level. Prompt engineering patterns reduce hallucination surface area at inference time. Guardrails validate outputs post-generation. And active detection methods like SelfCheckGPT provide consistency-based hallucination signals when other layers are insufficient. Combined, these layers produce AI systems that enterprise and professional contexts can actually rely on. In our next session, we'll shift from reliability engineering into advanced prompting craft. We'll master zero-shot and few-shot prompting, the techniques that let you direct model behavior with precision, without requiring fine-tuning or infrastructure changes. It's where the abstract principles of prompt anatomy from session 3.1 become concrete, repeatable techniques. I'll see you there.